So welcome back out there. I have no idea in the world who's going to see this. Probably, a few friends, maybe some family if I share it, maybe some trolls out there. I don't know. But welcome back. And I'm just doing I'll just repeat myself. I've said this in the intro of the other vids. I'm sort of doing this rubber duck programming where it's just a mythology I heard online where you sort of code or talk through a problem to an inanimate object, and by teaching something, the human brain, or we're able to sort of how we work, we're able to take in more information, understand things at a deeper level. So teaching is the best form of education. Basically that's the theory I'm going off. It spoke to me. I enjoy it. I do enjoy teaching when I can, and it does help me learn the most. So it spoke to me. So I have a little rubber duck in front of me here, and I'm, putting it out there, and I'm sharing what knowledge I have on coding and programming for whoever the hell on YouTube is out there. So this next algorithm we're learning that I'm, teaching and selfishly relearning myself because sometimes you don't use these often every day, is the binary search. And the binary search speaks to me because the moment I saw the binary search, I knew sort of what it was doing, because in my time, I was a reservist for about 8 years, I believe, or 7 or 8 years, and in the Canadian Armed Forces. And I took it quite seriously, and I spent a lot of time in the summers. Sometimes they call the reservists the weekend warriors, but I did spend a lot of time in regular force bases in the summers, and took all the training courses I could. And we were an armored regiment, and in the armored regiment, you have to learn the binary search, although they don't call it the binary search. They just talk about learning gunning and learning how to hit the target, and sort of gunning techniques. And the gunning technique that they taught us, and now this is in the 90s, so this was way before modern M1 battle tanks and modern Leopard tanks out of Germany, where they have lasers to help get you onto the target with 90% first round hits. But in the 90s, they were still teaching old mythologies, probably dated back to World War II, where you would fire your tank at your best guess. So the best guess you got on your first round, the better for the better for your team, better for your side. So you'd just make a random guess at the distance from the target was away. You would do your best. You would sight the target in, guess on the range, and fire a round. And hopefully it was a tracer round so you could see it go down range. And when that round, you would observe where it was critical that you observe, because you needed to observe where that round went. And if that round went too far, then you would have to lower your range. And if it went too short, you would have to increase your range. And they always told us that once, it doesn't matter how far, or it doesn't matter, they taught us that it doesn't matter how far or how short you shot, it's just whether you just shot short or far. And you were supposed to raise or lower the gun by 250 meters. So if you shot long, you would lower 250 meters. If the second round hit long again, you would lower another 250 meters. And you would keep lowering until you were short. So the idea was not to keep guessing. That's what they had taught us. Don't keep guessing. That the binary search, which is about it's close. Binary search in programming is halving your problem. So search half of the data set each time. That's not exactly what's being taught here, but it is. There's a similar concept where you don't guess, and you keep sort of lowering by a specific increment a distance in meters to the target until you hit. And so you were sort of forced to let's reset this. It kind of shows it. So if we fire a round it's short. So the next round we have to fire is long by 250 meters. Now that's a pretty ridiculous example. Maybe we could reset and do this again because that was pretty, okay, it's on a repeat. So that was pretty long, the second one. So now you would lower by 100 meters next time. So each time you would just lower the increment. So if you were short, you raise 250, and then you lower by 100, then you lower by 50, and then you yell out target when you hit that target. So then we lower by 50 again, target on. And once you're target on, you just stay there and keep, where it says we're short here, but probably by 10 meters. But, you just keep staying on the target from there. So hope that makes sense. It's a long-winded way of saying that, there was a version of the binary search that spoke to me when I first heard about the binary search. So let's get into the binary search. Okay, let's create our function. Okay, so let's get into the binary search. First thing I just want to call out is that the word binary here does not mean the zeros and ones that make up a bit. It's not binary. It's not binary numbers. It's not base 2. Counting in binary. It means halving. It means halving. Each iteration you're going to half the data set, and you're left with 2 halves, and you have to make a decision whether you want to work with the right half or the left half. That's why it's called binary search. At least that's why in my mind. So that one can confuse people by calling it binary when we're not really manipulating binary. The second thing to note is that we're working with sorted data sets. So the array must be sorted first, otherwise this doesn't work as speedy as it does. So keep that in mind. And thirdly, a lot of times, the leak code and the interviewer or whoever you're just trying to teach binary searches, are looking for the index where the target was found. So that is something we sort of need to Java doc in the function, so to make that clear. Otherwise, the way if you don't have that in mind, what you're going to return is going to be confusing. So demonstration of a binary search. And so the target, the data set in which to search, and the target is the index in which the target was found. Okay, so that's important. Oh, sorry, no, that's the return value. So return value is the index in which the target was found, and the target is the value to search. Okay, so let's keep that in mind here before we get into the code. So let's get into it. So again, I'll keep falling back to this diagram. So the first thing we're going to do is set up the 2 ends of the array, find the index at the beginning and end of the array. So int left equals 0, int right equals array.length minus 1. And for the longest time, I let this confuse me. Oh, why do you minus a 1 all the time? And that's because you have to remember that when you when in other language, this is almost, you could think of length as size as well. This is returning the size of the array, the length of the array, or size of the array, not the index. So that's why. So this is arrays are zero-based indexed in Java. So this array.length is going to be 1-based. So it'd be 1, 2, 3, 4, 5, 6, 7. But we want index 6. So it'd be 0, 1, 2, 3, 4, 5, 6. So we have to minus 1. You'll get used to it, but just keep in mind that length returns a size. Let's keep iterating and halving until we find the answer. So when left is less than or it's equal to right. The equal is important because we want to search. We want to continue the search on every element up until we find it. We want to include the value when it gets to the middle. Okay, so let's find the midpoint. So int mid equals left plus right divided by 2. And that will get us the midpoint, the mid index in your array. And so we're halving our data set in 2. Now keep in mind a couple things. You should note, if you're used to coding Python, you don't worry about this because in Python, a number will grow as large as you let it grow. And they even have this cool / solution, double / solution, where it'll floor the number so that you never hit the decimal. In Java, in int's an int, so we don't have to worry about that. When we divide ints, we'll get ints. But you do have to worry about the size of the int in Java. And if you're in an interview or if you're being asked to code this or if you're doing this yourself in LeetCode, the most important thing is you understand that there is a constraint on the size of an int. So think about that when you're coding a solution. You may have to break your array up into smaller arrays, or the library you're working with, but you only have 4 bytes to work with this. The extremities of the ints of the numbers that you're going to be working with are these. As you know, so Java, this is the primitive type int is a signed. Is a signed integer. Signed means that the first bit is either 1 or a 0, denoting whether it's negative or positive. And an int is 4 bytes, 32 bits, and this is the range which you can work with. You can hold that number. So to help us ensure that we stay within this number, almost guarantee that we stay in this number, we're going to change this a little bit. Again, you won't have to do this in Python. So left, right, minus left divided by 2. So what this does, it prevents what they call integer overflow, because once you overflow, the first bit will be flipped, and once it's flipped, you will get a negative number when you didn't expect a negative number, and it can cause a nasty bug. So instead of adding 2 large numbers together, here we'll calculate the smaller difference of right and left, then half that, and then add it to the left. So first operation is here, where we just find the difference, divide that by 2, and then add it to the left. Okay, if that makes sense. So I hope that helps. Let's continue. So the next thing we want to do is test whether this at this index, whether the target value that we want to find is found at that middle point. So if array mid equals the target, then let's get out. We will return our index. Again, we're returning the index in which the target was found. Boom, we're done. Now what's the chances we do it on the first time? Probably slim. Okay, so if that condition doesn't exist, where the value found here equals our target, we'll continue. The code will continue. The function will continue to the next statement. So if the array at this index, the value found in this array at this index, if it's less than the target, then we know we have to search the second half of the array. So let me make that clear. So if the value found here is less than the target, so let's use our image. So if the value found here, is less than the target, then we know that the target must be found in the right half of the array. So we have play that back if that was confusing. So left equals mid plus 1. Else, if the value was greater than the target, then we need to search the left half of the array. I hope that makes sense. So and we'll do that by shifting the right index. So right now equals mid minus 1. So in that situation, we'll search from 0 to 3. We'll search the numbers here. And if we didn't find our answer, then let's return negative 1. Okay, that is basically the magic behind the binary search. Let's run it and see if this magic works. Any bugs? So I wanted to find the target value of 5. And it says it found it at index 2. So if we look at our array, index 0 is 1, index 0, 1. Yeah, index 1 is values 3, and index 2 values 5. So we did find our target. Let's try it again with target 4, negative 1, therefore 4 was not found in the index. Let's try with 7. Run it again, and it says it found it at index 4. And that's it. That's the magic of the binary search. Hope that helps someone. I know that like I said, this is done better than perfect. I'm not editing these videos. These are raw. There's a lot of ums and hums. But again, what's this import doing there? You're seeing it live, and I hope this helps someone. I truly do. Ciao, ciao. On to the next.